So now that we understand the way in which optimal solutions must be composed of optimal solutions to smaller subproblems, we're well positioned to turn that into a recurrence and then a dynamic programming solution for the knapsack problem. To compile our discussion from last time into a recurrence, let me just introduce a little notation. So by capital V sub I x, what I mean is the maximum value you can get of a solution that satisfies two constraints. First of all, it should make use only of the first I items. Second of all, the total size of the items that you pick should be at most x. The analog of this notation in the independent set problem was G sub I, the graph with the first I vertices. We're now using two indices instead of one because subproblems have two different ways in which they can get smaller. Recall case 2 of our thought experiments. When we look at a smaller subproblem, there was both one less item and there was also less capacity. So when thinking about a subproblem, we need to keep track of both. We need to keep track of how many items are we allowed to use, and we need to keep track of what's the total size that we're allowed to use. So let's express our conclusion of the last video in this notation. What did we figure out last video? We figured out that the optimal solution has to have one of two forms. Either you just inherit the optimal solution from the knapsack instance with one less item. That was the first case. Or you take the optimal solution to the subproblem which has one less item and less capacity by the weight of the current item, and you extend it to an optimal solution for the current subproblem using the ith item. So V sub I comma x, the optimal value for the current subproblem, it's the better of the two possibilities, so we take a max. The first possibility is just the optimal solution with the same capacity and one fewer item. We're using that solution. The second one is you commit to using item I, you gain value Vi. And you combine that with the optimal solution using the first I minus 1 items and the reduced capacity of x minus the weight of the current item. So one quick edge case, if the weight of the ith item is bigger than our permitted capacity x, then of course we can't use it, and then we're forced to use the first case. We're forced to be in case 1. This then is our recurrence for the knapsack problem. So that completes step 1, where we think about the optimal solution structure and use it to devise a recurrence. Now in this step 2, we're going to precisely nail down what exactly are the subproblems we have to care about. Well, in our maximum weighted independent set example on path graphs, remember the reasoning. Every time we recursed, every time we needed to look up a subproblem solution, it was obtained by plucking vertices off of the right of the graph. And for that reason, all we ever cared about were the various prefixes of the graph. In one dimension, we've got something similar going on here. Whenever we look at smaller subproblems, it's always with one fewer item. We're always sort of deleting the last item before we do our lookup. So again, we need to worry about all possible prefixes of the items. So subproblems of the first I items for all values of I. For the knapsack problem, however, there's a second sense in which subproblems can be smaller. And remember case 2 of our thought experiment. When we want to know the optimal solution that's guaranteed to use the current item I, we have to reduce the capacity before looking up the corresponding optimal solution of a subproblem. That is, we're not just peeling off items, but we're also sort of peeling off parts of the knapsack capacity. Now here is where we're going to use our assumption that I told you at the beginning in our input, that sizes are all integers and that the knapsack capacity is an integer. So the knapsack capacity starts at capital W every time we peel off some integer amount of capacity from it. So at all subproblems, we're going to be working with integral knapsack capacities. So therefore, in the worst case, what are the various subproblems that might arise? Well, perhaps each choice of a residual capacity, 0, 1, 2, all the way up to the original knapsack capacity, capital W. So now we're in great shape. In step 2, we figured out exactly what subproblems we care about. In step 1, we figured out a formula by which we can solve bigger subproblems given the solutions of smaller ones. So all that remains now is to write down a table and fill it in systematically using the recurrence, beginning with the smaller subproblems, ending up with the largest subproblems. So here's the pseudocode. It's again going to be very simple. In this algorithm, the array A that we're going to be filling in has 2 dimensions, in contrast to the 1 dimension in the weighted independent set problem. That's because our subproblems have two different indices. We have to keep track both of which set of items we're allowed to use and also what capacity we need to respect. So the two independent variables indexing subproblems forces us to have a 2D array that we're going to go through now in a double for loop. So in the initialization step, we fill in all the entries where I equals 0, where there's no items. There, of course, the optimal solution value is 0. And then we just go through the subproblem systematically. When we get to a subproblem, we use the recurrence that we developed to compute the entry in that table using, of course, the entries that we've previously computed in earlier iterations. So for a given subproblem where you're allowed to use the first I items and the residual capacity is X, what do we know from our thought experiment? This can only be one of two things. We're just going to do brute force search through the two possibilities. The two possibilities, well, we have case 1 where we just inherit the optimal solution with one fewer item and the same capacity. Or if we're going to actually use item I, then we compose that with the optimal solution from the first I items that leaves enough space for item I. And in that case, we get the value v sub I for including this ith item. So this code doesn't quite make sense in the case where the weight of the current item wi is strictly bigger than the capacity x. That would give us a negative array index, which of course is a no-no. But in that case, amongst friends, we just interpret it as ignoring the second case of the max. So, I'm not going to write down the extra code, but what you would write down is if wi is strictly bigger than x, then you just define a of I comma x to be equal to a of I minus 1 comma x. And one crucial point is that, by the time we need to solve subproblem with a given I and a given x, we have at our disposal the solutions to all of the subproblems that we need. In particular, in the previous iteration of the outer for loop, we computed the solutions to the two relevant subproblems for evaluating this recurrence. They're there waiting for us, available for constant time lookup. So after this double for loop completes, sitting there waiting for us in in the entry n comma capital W is the solution that we wanted. That's the max value solution that can use any items that it wants and that can use the entire original knapsack capacity capital W. That's what we want to return. So that's it. That's the whole dynamic programming solution for the knapsack problem. Just to make sure this makes sense, in the next quiz, I want to ask you to analyze the running time of this dynamic programming algorithm. All right, so the correct answer is the second one, and the running time analysis is as straightforward as it was for the max weight independent set problem. We just count up the number of subproblems and look at how much work we do in each. So how many subproblems are there? Well, they're indexed by both I and X. There are n plus 1 choices for I. There are capital W plus 1 choices for X. So that gives us theta of n times W different subproblems, and all we do for each is a single comparison amongst previously computed solutions. So we just do constant work per subproblem, giving us the overall running time of n times capital W. So a couple other quick notes which play out in exactly the same way as for the max weight independent set problem, so I'm not going to discuss the details here. So first of all, correctness. Again, it's exactly the same template as in the previous dynamic programming algorithm and in our divide and conquer algorithms. You just go by induction on the problem size, and you use the case analysis or a thought experiment to justify formally the inductive step. So this algorithm suffers from a similar drawback to the max weight independent set algorithm for path graphs that we looked at. Namely, it computes the value of an optimal solution, not the optimal solution itself. It returns a number, not an actual subset of items. But just like with the independent set problem, you can reconstruct an optimal solution from the filled-in array just by tracing backward. So the intuition is, you begin with the biggest subproblem and you look at which of the two cases was used to fill in that entry. If case 1 was used, you should exclude the last item. If case 2 was used, you should include the last item. And also which of those two cases tells you which subproblem you should trace back to continue the process. So I encourage you to spell out the details of this reconstruction algorithm in the privacy of your own home. That'll give you some nice practice with this reconstruction aspect of the dynamic programming paradigm.